Okay, well, really what I want to do in this discussion session is just to take questions. I can also say a few words about the factorization paradox that I didn't get to in the lecture, but let me start with questions, and if we get a dead spot, then we can I can talk about factorization for a minute. So I guess the easiest way is just to well, either just shout it out or do the raise hand.
Okay, let's see. Okay, we have a raised hand, too sure.
Hi, so I wanted to ask, like, after this page time, we have this change of like saddle point dominance, and because of that, we get this page curve. Now, does something interesting happen at Poincare timescales, or does it just stay this way till, let's say, large times? For the eternal black hole setup, like it saturates the entropy of the radiation, saturates to some value.
Yeah, let's see. Yeah, so Poincare timescales are way off this plot, exponential and entropy. This calculation does not see anything there. I mean, it doesn't know anything about something special happening in the Poincare time. I don't think I have anything useful to say about that. I think it's an interesting question whether semi-classical gravity knows something useful about that time scale. If I had to guess, you might have to well, I don't know the answer. If it does, then you have to include sums over topologies. I don't think there can be any individual topology that knows about that time scale.
Right. So the dot 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 that you were writing, all of those terms, we would have to sum over that, right? Is that what you're saying? That all of them at late enough times, yeah.
Yeah, and if we could do that in quantum gravity, like in the full UV complete theory of quantum gravity, then we would certainly learn about the Poincare recurrence. But I guess the real question is whether you can detect it somehow in the low energy effective theory. And I don't know the answer to that.
Okay, thank you. And one more just small technical question. So here in this calculation, at one point we were computing SCFT of B, the region which is the complement of R union I. So,
yes.
Right. So for R, I agree that we can use one Neumann entropy because, well, gravity is very weak and we can just use our classical QFT formula. But B, it's kind of tricky. I mean, are we dealing with we are dealing with dynamical gravity in the B region. So what does SCFT of B mean?
Yeah, so it's important that in the island formula, it's a little, right, the island form is a little funny because the left-hand side is supposed to be calculating a von Neumann entropy in quantum gravity. But on the right-hand side, we have this SCFT. Okay, so, and this came from derivation, but SCFT means, the definition of SCFT that came out of this derivation is that you should calculate it using ordinary semi-classical gravity on fixed topology.
I see.
Okay, that was just what came out of the derivation. That you should do this just using ordinary quantum field theory in curved space. Not you shouldn't like now use wormholes again to calculate this term, right? So this term was just by definition the matter entropy on a fixed curve background. So there's no problem there.
And the left side is the exact answer which we would have gotten, like if somehow someone magically told us the exact quantum state.
The left hand side is, well, it's not exact. It's leading term it's the leading term at large n or small g Newton.
Yes. Okay. Okay. Thanks. Thank you.
Okay. I think Anirudh.
Anirudh. So hi. This is a clarification question. So when we were doing the calculation for the R region, entanglement entropy for R region, and then we introduced wormholes. Now we used to use the branch cuts to like cover the whole thing. The only doubt which I have is that why should we like try to find it for R union I, not just R? Why does the inclusion of branch cut make us like do the calculation for the union of both the regions?
Well, what happened in this calculation was that we're trying to calculate the path integral on this topology.
Mm-hmm.
And that has two contributions. It has a gravitational contribution, and it has a quantum field theory or CFT contribution.
Yes.
Okay, and we separated those out. So the CFT term was the path integral, was the CFT path integral on this manifold.
Okay.
And that is, so now you can go back and calculate the CFT entanglement entropy on I union R by the replica method.
Mm-hmm.
What you would do is you would write down this exact manifold and in order to do that calculation.
Okay.
And if you just went back and did SCFT of R, you wouldn't, this is not the manifold you would use. This is the manifold that appears in the replica calculation of entanglement entropy on I union R. So that just came out of this calculation that we were doing.
Okay. I had like one more question. Like, are we like you said that to see the paper by Maldacena and Lukowitz for generalized entropy? So there, I mean, do we assume ADS-CFT? Means that's an assumption for doing the calculation?
No, not really. I mean, well, I really just so their paper has a local analysis of the contribution of the gravitational contribution around this twist point.
Mm-hmm.
That's the part of the paper that I was referring to. It turns out that the gravitational contribution to this partition function is localized at the defect as n goes to 1.
Mm-hmm.
Away from n equals 1, there's some complicated gravitational contribution. But as you take n to 1, the only gravitational contribution is from the defect, and then the asymptotics don't matter. So their paper really applies also to the asymptotically flat case.
Okay, thank you.
Andre?
Hi, Tom. I have two questions. First is probably somewhat naive, but when you draw the cylinder, which is the Euclidean black hole, the horizon is at the bottom there. And as far as I understand, when you do the Euclidean surface, there is no interior of the black hole. This point below stops at the horizon. And it's not clear to me how this branch cut that you draw, how does it record something that is inside the horizon, which is what you're calling the region I below?
Good. So part of the answer to your question is that in the eternal black hole, the endpoints of the island are actually outside the horizon.
Right. So,
okay. So the way to think about this calculation is that the pictures I was drawing in Euclidean are all taking place in the Euclidean continuation of the t equals 0 slice. So all the picture in the Euclidean pictures, region R lies on this time slice. And then after doing that, after finishing the calculation, get all the way to the end and have a formula for both the entropy and for the endpoints of the island region. We take that final answer, analytically continue it to Lorentzian values of x2, the endpoint of region R. And that is then interpreted as the calculation at later times. Okay, so what's happening is that region I is initially defined in Euclidean, but then when we analytically continue, we end up with a region that goes inside the black hole. Now, this becomes more subtle if we talk about the collapsing black hole, because the collapsing black hole doesn't have, let me see if I think I have a picture of the collapsing black hole. Here it was. Okay, so the collapsing black hole never has an island that sticks outside the horizon. And the Euclidean interpretation of the collapsing black hole is pretty subtle. But you can analyze the collapsing black hole in Euclidean. You just have to insert some operators into your Euclidean path integral that account for this shock wave that forms the black hole. And what you can do is you can define this saddle point as a Schwinger-Keldysh path integral. So a Schwinger-Keldysh path integral is a path integral that starts in Euclidean, evolves to the Euclidean time equals 0, then evolves forward in time. Then you insert some operators or whatever you want, and then you evolve backward in time, and then you evolve around the Euclidean circle. So sometimes people draw these Schwinger-Keldysh path integrals like this. They have a Euclidean circle, and then they have a Lorentzian piece that's folded. Okay, so this is Lorentzian, and this is Euclidean, and you can define the entire path integral this way and the entire saddle point this way. You get a complex saddle with both Lorentzian and Euclidean pieces, and then you can end up with these islands being inside.
So, okay, I think I understood the part of the non-collapsing black hole. This part there, right? I don't know if I can follow, but so when you say that the island never reaches outside the horizon in the collapsing black hole, does the point, the region of the island, this extremal region which you were calling, I don't know, X2, I believe, in the other side. Anyway, this point, does it appear as a result of calculations, or it has to, right?
Do you mean this point here?
You postulate the outside region, and then you can calculate the inside region.
Yeah, that's right. In all these calculations, region R is being chosen. We just pick a region R, and then we do the path integral for the replica calculation for its entropy, and then this point over here comes out of the calculation. We don't put that in.
All right. Okay. Yeah. When you connect the two cigars, it must appear somehow, right?
Yeah. The way to think about it is that in the replica calculation, this region I is sort of fattened out into the tube that is the wormhole. But as you take n to 1, the tube really just shrinks to a cut. It kind of pinches off. The tube kind of pinches off, and you just get this interval I is all that's left when n is equal to 1.
Okay. Okay, thank you. I had another question. I don't know if there's time, which is somewhat more conceptual. Um, uh, what does this say about proposals like fuzzballs? Because as far as I can tell, I have Mathur's theorem that says that you have to modify the horizon. As far as I can tell, you modify the horizon, but the fuzzball doesn't have the interior of the black hole, so this cannot be very compatible, both approaches, or is it? I don't know. That's the question.
Yeah, this does not fit into the fuzzball picture. Well, fuzzballs can mean many things. I'm gonna pick one of them. So I would say it this way. So Hawking's calculation tells us this. Okay, so it tells us the leading term is rho thermal, but it doesn't tell us anything about the perturbative or non-perturbative corrections. Now, Mathur's theorem makes clear that the perturbative corrections, the perturbative piece doesn't help. And not only does the perturbative piece not help in this argument is very general. It just uses quantum information. And so it's very robust. Like even if we modify the dynamics near the horizon in some small way, no matter what we do, it will never help. Okay, so that's Mathur's theorem. I think that roughly speaking, the idea that these perturbative corrections couldn't help was really known since the beginning. That's why it was called a paradox. But Mathur's theorem sharpened that and made it totally robust. And that leaves us with two options. Okay, so the two options are these. Well, one option is to rely on these non-perturbative terms. I think Mathur would call these non-local. I would say that yes, they're non-local, but in just in the way that we would expect in quantum gravity, which is a theory of fluctuating geometry. So there's these. So that's one option is to rely on these non-perturbative terms. The other option is to just replace the black. Just say there is no black hole. There's a fuzzball. There's something else, and the Hawking's calculation just totally doesn't apply because it's a fuzzball, not a black hole. And that seems to work in some cases with enough supersymmetry. Of course, in that case, you're left with a new puzzle to solve, which is well, what's the role of the black hole then? Are there actually does it feel like a black hole when you fall in, or does it feel like a fuzzball? And that I think is a hard question that you then have to address. But yeah, those are sort of the two options. You either make a large modification of physics near the horizon, or you rely somehow on these non-perturbative effects. And the wormholes are choosing the non-perturbative, are using the non-perturbative effects. Did that answer your question?
Yes, totally. Yes. Thank you. There are some, I haven't read them, but in detail, but there are some papers, recent papers by the fuzzball people that precisely addresses this question of what happens when you fall inside the fuzzball. Well,
yeah, there are. It's certainly a problem they've worked on and thought about. I don't think it's they have proposals. I don't think it's really been settled though.
No, yes, I agree. I don't think. Well, thank you, Tom.
Okay, we have a question from Tushar.
Hi. So I had 2-3 more questions. So I was just wondering, like, should I ask them now, or will you describe that factorization problem and I should ask later? Some speculative questions. I mean, so maybe you should.
Yeah, I'll mention the factorization thing, and then we can see if anybody else has questions and come back.
Okay.
So the factorization paradox, I just wanted to mention, so this is something people are very interested in lately, so I wanted to mention how it's related to replica wormholes. So factorization paradox is a problem that you have when you go to calculate something not like trace row squared, which is what we've been calculating, but trace row quantity squared, so trace row times trace row. Now, if you go to calculate trace row times trace row, then there's an obvious contribution, which is 2 copies of the Euclidean black hole. But you might wonder if there are contributions like this. These contributions have the right boundary conditions, so it seems like maybe we should include them in the path integral. And there are even some situations, not the simplest one, like what I've drawn here, but there are other situations with non-trivial matter content where there are saddle points that look like this. And if you find saddle points like this, that's very perplexing because you try to calculate something that was obviously, where the answer is obviously supposed to be just the first term. There can't be any connected contributions, just a number times a number, and it has to factorize into a number squared. So if you find terms like this is very confusing. And this is known as a factorization paradox or problem or puzzle, and it's what led people recently to discussions of things like ensemble averaging. See, if you think of these. If you think of this theory as being a disorder average, then the disorder average can effectively couple the two systems, and then you can get things that don't factorize. And there's discussions of things like baby universes in this context. Now, the replica wormholes that we discussed do not have this problem because we did not calculate a quantity squared. We calculated trace of row squared. And in terms of these path integrals, by gluing together when we glued together region R, so we didn't do the path integral that's drawn, we did the path integral with these additional cuts here, which glued together the boundary conditions. So by gluing together things in the asymptotic region, we expect the answer to not factorize, and indeed it doesn't factorize. So there is no factorization paradox for replica wormholes. However, there are very similar wormholes which solve almost the same set of gravitational equations of motion, which do have a factorization paradox. So even though there's no clear problem for replica wormholes, they seem to be related. Okay, so these problems do seem to be related to each other, and we could ask, well, why can we trust, or really, I think the most interesting question here is when can we trust the wormholes and when can we not trust the wormholes, and we don't really know the answer to that. We want to include the replica wormholes that give the unitary page curve, but we know that there are very similar situations where they have this factorization problem. So the question is, how do we make sense of that? Do we need disorder to make sense of those wormholes? Are there additional contributions that have been missed, or what exactly is going on? Now, a lot of the explicit calculations that have been done are in very simple models of gravity, like JT gravity without any matter. And most, possibly all, calculations with this factorization problem do not apply in a controlled way to a theory of gravity plus matter in more than 2 dimensions. In other words, these are in situations where there might be equally large, there very well could be equally large contributions to the path integral that have been neglected in situations where you get these factorization paradoxes. So that's sort of the loophole. The loophole in the factorization paradox is that there you really might have these ... dots, and you have to understand, or you want to understand how the ... dots restore factorization. Now, that's not to say that I said that it's not entirely controlled. That's not to say that these answers are meaningless. The answers that you get from these non-factorizing contributions turn out to be extremely interesting and appear to be related to the chaotic statistics of the energy levels of the black hole. So understanding these is really interesting. But I think people are still trying to work out to sort of disentangle the interesting contributions from these connected terms versus the ... dots, which are the same size, and trying to understand which ones you can trust and how to make sense of all this. So that's all I had to say about factorization. So now we can see if people have other questions, and maybe hold off just a minute, Tushar, and we can come back to you if other people don't have questions.
So Tushar, do you have a question about this?
Yeah, so I had a question about this slide. So, right, so if given the boundary conditions on the thermal circles, let's say we do the gravitational path integral, naively, isn't it intuitive that we should include from the gravitational perspective all possible geometries connecting these boundaries? So that will include this factorized, the 2 Euclidean thing plus this wormhole contribution plus other contributions. So does this sum, so I'm just trying to understand this. So the point is that does this sum from the boundary perspective, we expect that whatever contribution we get from this gravitational path integral, this should be the product of trace row of each of the individual boundaries, right? But that is what not happens, right? That's what you're saying.
That's right. That's the puzzle. Yes.
Okay. So right. So now other questions. So in this eternal black hole setup, the page curve got saturated at what value? 2 times S black hole?
Not quite. So let's go back to the slide. So the saturation here is at 2S black hole plus SCFT of B. Right, because what the 2 things we're comparing here are, well, sorry, we were doing min x over I, area of di over 4, plus the matter term, which we said was the same as SCFT of B. Okay, so when it saturates, it'll also have that contribution. And the way to think about that physically is that so when we calculate the entropy of R, the question is how much how entangled can R become? And the answer is that R can be entangled in two ways. It can be entangled with the black hole. That's the area contribution. But it can also be entangled with the quantum fields in region B. So both of those contribute to the flat piece of the page curve. It's fortunate that this other term is very important because it's infinite. So the contribution of S of B is infinite. And so that was crucial to get this to work because the entropy of region R is infinite, but that cancels. Yeah, this is really T plus infinity, and this is and then this term is infinite, but those infinities cancel, and that's what gives you a reasonable page curve.
You see, so right, so this will be right. It will saturate to 2 times as black hole plus SCFT, which is infinity. Okay, so SCFT.
Yeah, I've subtracted the same infinite constant off of both of these pieces of the curve.
Okay, but yeah, okay, so right, but so let us think from this, let's say the one-dimensional point of view. Let us say that in that picture, like, can you show the picture? So the above picture, thank you. So in this picture, if we draw, let's say, 2 vertical lines and think of it in the way in the islands paper thought of it, like there are 2 baths which is coupled to an ADS2 region. Can we think of it in that way? And then maybe replace this 2-dimensional ADS black hole by, let's say, SYK degrees of freedom on the boundary?
Well, in the RST model, we don't know how to do that holographic duality. So if we had been talking about if I drew these lines here and we talked about ADS2 black hole coupled to flat space, then yes, we would have a holographic duality we could use. We could delete the black hole and replace it by the SYK model. But in the RST model, we don't have that duality. So I don't know any other holographic way to do this calculation.
Oh, okay, thanks. So, right. Because, yeah, I asked this question because I was confused. Right, so, right, how do I frame this? So, yeah, so, right. So last year in April, there was a paper by Hartman and in which he talked about this new state which he was writing called the TMD state. And then are you familiar with that paper? Sorry.
Sort of.
So yeah, so in that paper at the end, he was mentioning how, let's say, this for that their usual setup, the JT gravity setup, this saturation cannot be at 2 times as black hole because then that will imply that the black hole degrees of freedom, the left-right black hole degrees of freedom are sort of maximally entangled with radiation. But this cannot happen because of the fact that there exists an ER bridge between them, and the fact that the stability of the bridge has to exist is some classical correlation or some mutual information is required for this bridge to exist. Therefore, he was claiming, I think so in my opinion, that this saturation cannot be at 2 times as black hole, but is maybe at S black hole. So I just wanted to understand that in this picture, but yeah, maybe this is not, yeah, setup is.
Yeah, I don't think I have anything useful to say about that. I didn't really understand that argument, so let me not say anything.
Yeah. And one another question was that, can there be, besides the 2 disconnected part and the wormhole geometry, can there be other saddle points which contribute to the Rene entropy computation that we do? But I mean, I'm not talking about the other, like.
So I think let's come back to this. I think maybe Alejandra had a comment about something else I said, because I might.
Okay.
Or was it a different question?
Sorry.
Do you know how to do holography for the RST model? Is that what you're going to say?
No.
Too bad. You raised your hand.
I'm happy to let Tushar finish asking his question, and then I wanted to ask you some other stuff.
Okay, sure. Okay, go ahead, Tushar. You were asking if there can be other saddles. Was that it?
Yeah, other saddles. So which is not like geometrically obvious.
Well, I don't see why not. I mean, I can tell you about one class of saddles that was studied in the Stanford replica wormhole paper and some follow-up work since then. And those are, well, first of all, as I mentioned before, this won't affect unitarity of the page curve. If there are bigger contributions, that means smaller entropy. So the page curve will still be unitary. But it would be very interesting to find those contributions if there are any. The kinds of contributions that were studied in this paper are contributions where you have many of these necks and only some of them are joined, like this contribution, for example. And there's a very large class of such contributions. And what they showed in that paper is that these things, at least in some cases, including in the model they studied in that paper, these things can be summed up. And what they do is they give a subleading contribution that smooths out the phase transition at the tip. That is, this corner in the page curve gets smoothed out by subleading effects in G Newton, and you can understand those as coming from the sum over the many non-symmetric contributions. I don't know if there could be other ones that are also relevant. It'd be interesting to find them.
Okay, thank you. Thanks a lot.
Okay, Alejandro?
Okay, my turn. Yeah, I had like two pretty, it's nothing very specific or technical, so, but I had two questions, but I first wanted to ask you, so they come in two different universality classes and you'll tell me which one you want to discuss first. One was related to the Fosbull issue, and the other one was related to this factorization problem. So what do you want to?
Well, since I'm afraid this might be the last question, let's start with the fuzzballs.
Okay. No, so the thing is that, fuzzballs, as classical solutions in supergravity, they exist, period. You have some 10-dimensional background, you decide to fix some charges, some mass, the solutions exist. And so from the point of view of how you were putting it, okay, there will be a big gravitational path integral, the expectation will be that these things will contribute to the gravitational path integral. But is it your intuition then? Because the way that you were answering the question just made me, I'm just trying to pick on your brain. They will contribute non-perturbatively, but you think that they will contribute very differently on how the replica wormhole will contribute? Is that we don't know how to treat them in a Euclidean sense, so I have no idea how to add them to a Euclidean path integral. They're very Lorentzian type solutions, but is your expectation then that they will be in the non-perturbative part, but in a very different fashion from the role that the replica wormholes are adding to things? Or are we more open-minded and it's we don't know, maybe? I guess you don't have to put this recording online if you don't want to.
No, it's not. I'm not trying to be careful. I don't think I really know what the answer is, but it's part of the reason it's hard to answer is that replica wormholes are a calculational trick. They're not right. They're not something that happens. Right?
Sure, but
it's a Euclidean path integral that's used to calculate the entropy. So it very well could be that in highly supersymmetric case, well, yeah, I guess it could be that in supersymmetric.
There are also fuzzballs that are not supersymmetric, but there's not that many. That's the only thing. But there are solutions that are not supersymmetric. Very few. Joseph has been working really hard to build them.
Right, but not enough to do a page
No,
curve.
I don't. My point is not if they're enough or not to reproduce the entropy. That's not what I care. It's like this is a configuration. Like it is a solution to the equations of motions. It's a regular solution to the equations of motion in Lorentzian signature. That's my only caveat. Like, so I know it as a Lorentzian solution, and it's like, okay, so what is its role in a Euclidean setup? Like,
yeah, I don't know the answer. I guess I'm not going to answer your question, but I'll add to it. Another question is like, you could say, okay, well, if both of these things exist, let's take some black hole where we know lots of fuzzballs. Both of these things exist. Now form a black hole by collapse in that theory, and which one is the more relevant one for those black holes formed by collapse? No, those aren't fuzzballs. They're some other state. Maybe there's some crazy superposition of fuzzballs or something. But which one is more relevant to the page curve in that problem? I don't know the answer to that. I'm not even sure we can make the question precise, just because if we want to talk about the page curve, we need things that are time dependent, and we need big page curves. So it would be hard to really study that question. But I don't think I have anything to say about it.
Oh, okay. And then I guess time's up.
No, I want to do the factorization one last. That's what I was.
Sorry. Okay. Okay. No, it was in the context. It's just that, you also phrased it in an interesting way that I think it's a little bit more open-minded. This whole discussion of, at least how I've heard the discussion of averages and ensembles, it feels like you're either on one side or the other side of the how do you think about the factorization problem. But but like we do have examples, like for instance, connecting to, since Matthias was giving lectures here, Lawrence Ebenhardt, you probably you know this, like he doesn't see any evidence, like, okay, if you compute, well, he hasn't done the more difficult computation in a higher genus Riemann surface, but okay, from the torus side, like he doesn't see evidence that this factorization problem arises on the string world sheet path integral. And connecting it to your thought, it could be that for a theory of quantum gravity to be UV complete, you have to get rid of this factorization problem, as you were saying, like that the dots here are important. And so then it also made me think, so that was like one point, like you could advocate from a string theory point of view of like, yes, this is just an artifact of some low energy, like incomplete theory of gravity. It is very, in ADS3 is very strange because it's so natural to have these handle body type, well, not the handleables, but having like this extra like solutions. But then from the point of view of like, you remember back in the day when we studied the Ising model? I know it's
Barely,
not,
but yes.
but it doesn't really connect to this. Like you do have in mind that there's some low energy description, and in that case it doesn't. But in some sense, there's a way that you can set up holography where you say, I'm not averaging over the CFT, and I just want to like attach the CFT to a given, like I want to write it in a dual way. And so that might indicate to you like, okay, there's just some saddle points that are not allowed. Yeah, I guess you want a gravitational explanation of why those are not allowed, and not like saying like, okay, the CFT has to be dual to something. Okay, figure out what that something is, and if that defines gravity or not.
I think that used to be my point of view, that if you had asked about these wormholes a few years ago, I would have said, well, we we don't know how to do the path integral, and there's papers that say this. I'm not making it up. There's like famous papers that say this. They say like, well, we don't really know how to do the path integral in quantum gravity, so we don't know what the contour is in field space, and we don't know which saddles should be included. So we don't like these saddles. Let's not include them. But now I would say that was probably too quick, even in the cases where we don't like them. And so, well, I don't know if this is right, but what I think is probably happening is that these type of saddles, these factorization problem saddles, are an artifact of the low energy theory. They are canceled by the ... dots, but they contain useful information about the UV. These can both be, I think that's what's so interesting about this, is that I think they're both true. And the picture, well, the picture we understand for how this could work, well, I think the clearest picture is this recent paper of the Stanford group, where they talk about a single instantiation of the SYK model. And I think that picture could be general. So the picture is that the UV complete theory has two types of contributions. It has these contributions, which are self-averaging, where the average answer is actually equal to the true answer. And then they have ... dots, which restore factorization, but are not equal to any kind of average calculation. So that's really interesting because you get to keep factorization, but you also get to learn something from wormholes, which I think is like the best of both worlds.
All right, I think
Oh, yeah, then fine.
I will end this interesting discussion, and even though I'm a chairman, I will not allow myself to make further questions. So let us thank Tom again for a series of very interesting lectures and for the discussions. And well, I wanted still to make a couple of closing remarks, and I wasn't probably very clear in the beginning of Tom's discussion, but I have a slide, so which helps basically to say everything that I wanted to say. So Tom, if you allow, I will share my screen. Right, so I have this. No, that's not what I'm supposed to show. Oh, okay. So yeah, so I wanted just to say a few words. First of all, that originally this was not planned as a school. It was supposed to be a workshop. And there's a tradition in recent years to have pre-strings workshop before strings in some nice place. So we wanted to organize it in Natal at the International Institute of Physics. So this is how it was supposed to be. But as we know, it didn't work. And then the idea was to, okay, how can we make it useful? And also given that people are quite tired of all these Zoom talks. So we decided to have a school instead. And so this is the people I would like to, sorry, can you see that? Not sure.
Yes, we are seeing it. It's not full screen, but we are seeing it.
Yeah, I think when I tried full screen, it's showing myself instead of. Okay, I think it works now. Okay, so yeah, first of all, we, with the help of the advisory committee, we needed to decide on which topics to discuss, and the idea was, of course, some relevant topics for the strings that will happen next week. And we ended up in a number of topics, which was, I think, about 12. And it was also a difficult task to decide on which ones that we select. So with some input from advisory committee, we ended up in 5 topics. So here's our string quintet and also a solo by Bob. So in the order of appearance, we had very nice lectures by Matthias Gaberdil, who told us about his recent progress in EDS3 CFT2, and then a review of conformal bootstrap by Magdalena. Actually, then lectures of Anna Maria later, they nicely connected to that, and the story about celestial holography apparently can use some of the ideas of bootstrap, as we saw. So there was a series of very nice lectures by Anna Maria, very detailed ones, and I think we can come back to learn stuff from these lectures. Well, Tom told us about the progress in understanding the information paradox and all these nice ideas and connected to a general program of quantum gravity. And we had lectures by Clay, who explained that many things that we knew before about symmetry is not enough, so we need to come back and review stuff. And Bob gave a very nice complementary discussion sessions for lectures of Gaberdil. So we're really thankful for all the lecturers for preparing this set of lectures, and that's probably was much harder job than organizing this conference, this talk. And of course, there were some people that helped us to organize, and Valdelino is the main person behind the Zoom, and he really made this whole thing run smooth, and we're very thankful to him. And Giuliano is our designer, so he did this very nice poster. And Steve Nisio and Bia, there's this regular team that helps to organize conferences, so they also help us. We're grateful to them. And finally, we had unexpectedly, maybe, we had very nice participation. So there was more than 500 people, almost 600 registered. And so this is the low estimate is 300. This is the what we saw at Zoom at the peak value, but some people left and came back. So some people preferred one. They were interested more in the one lectures, and they didn't show up in the others probably. So that's kind of an estimate. And we're very thankful and very happy that our participants were active and they asked many questions, and they participated also quite active on Slack. So thank you very much for your interest and for your participation. And finally, of course, I would like to thank my co-organizers. So Tiago and I were local organizers, but I would like to thank Bruno, Alejandro, and João for their help. And it was really a very nice experience organizing this school with them. And out of local organizers, I want to especially mention Tiago, who was really a person with the initial idea of this conferences, and he did the most hard job in the preparation of this conference. So thank you all, and I wish you nice weekend and also nice spring conference. And I think we are better prepared now for the talks next week. Thank you very much. Well, if any of organizers want to say something, please.
Thank you, Dimitri. You did an excellent job too.
Thank you.
It was a pleasure working with all of you.
Yeah, I echo what Alejandra said.
Yeah,
I'm not really.
Thank you, everybody.
Oh, Tiago, you're here. Okay, great.
Yeah. Thanks everybody for.
Although I'm not really an outsider, right? I mean, almost local, I guess, next to local, perhaps. But thank you, Dimitri. Thank you, Tiago. Thank you, Alejandra. And hopefully João will get a recording of this, so thanks to him as well. It was very nice working with you. And thank to all the participants who made this very vibrant and, well, affluent, I should say, school. I hope everybody enjoys. It's very helpful for people that will watch main conference next week. And I mean, also, I guess that the lectures also merit an extra round of applause, because without them, there would be no school. So thank you all for the hard work. And also the technical staff like Valderino, who also helped us a lot.
Thank you, Bruno.
Okay.